How would your life change if you could see all dimensions at once? What if your perception wasn't limited to length, width, and height, but extended into realms we can barely imagine? In today's video, we're diving deep into the incredible idea of higher dimensions and asking, what would reality look like if we had access to all of them at the same time? Chapter 1. Gravity. For hundreds of years, gravity was a big mystery. People saw that it made things fall and kept planets moving, but didn't know why. Then Sir Isaac Newton came along and gave us a formula to predict how gravity works. Thanks to him, we could explain why apples fall and send rockets to the moon. But Newton couldn't explain how the sun pulled on the Earth across empty space. Then Albert Einstein changed everything. In the early 1900s, he said gravity isn't really a force. Instead, it happens because mass and energy bend space and time. Imagine a heavy ball on a trampoline making a dip. Smaller balls nearby roll toward it, not because they're pulled by a string, but because the surface is curved. That's how gravity works, Einstein said. Big objects like stars and planets bend space-time around them, and other objects move along those curves. This idea completely changed how we think about the universe. Suddenly, gravity wasn't some invisible force acting at a distance, it was geometry. The shape of space itself was doing the work. It was a breakthrough that reshaped science forever. But that's not the end of the story. This discovery opened up even bigger questions. What happens near black holes, where space-time bends to the extreme? What about the tiny hidden dimensions some scientists believe are curled up all around us? Let's keep going, because things are about to get even stranger. Chapter 2. The Fifth Dimension. Theodore Kaluza proposed a bold idea. If gravity is geometry, could other forces be geometry too? He took Einstein's equations and extended them into a fifth dimension, a second time-like or fourth spatial dimension. The result? Magic again. From his five-dimensional equations, Kaluza didn't just get gravity back. He also got Maxwell's equations, the laws that describe electricity and magnetism. This suggested electromagnetism could be explained as ripples in a hidden fifth dimension. For a moment, it seemed we had found a unified field theory. Einstein himself didn't object. The math worked. It was elegant. But then, things got weird. Chapter 3. Klein's Twist. Oscar Klein improved on Kaluza's idea by saying that the fifth dimension isn't big or something we can see. Instead, it's very, very small, so small that it's curled up tightly at every single point in space, kind of like a tiny invisible circle sitting on top of our normal world. Think of our universe as a big flat sheet of paper. Now imagine that at every spot on this paper, there is a tiny little loop or circle. These circles are so tiny that we can't see or feel them, but they are there. Klein suggested that electromagnetism, the force that makes magnets stick to your fridge and lets electricity flow, lives inside these tiny loops. While this idea made sense in math, it didn't match what we actually see in real life. When scientists use this theory to predict things like the mass or weight and charge of electrons, the numbers didn't line up with what experiments showed. Because of this, the Kaluza-Klein theory slowly lost popularity. But even though it wasn't completely right, the theory left an important mark. It showed us that extra dimensions beyond the three we know could be real, not just made-up stories in science fiction. These hidden dimensions might hold the secret to understanding everything in the universe. Chapter 4. Living in Flatland. To wrap our minds around the idea of extra dimensions, physicists often turn to Flatland. This imaginary two-dimensional world is inhabited by flat creatures. They have length and width, but no concept of height. Now imagine a 3D sphere passing through Flatland. The Flatlanders see it as a circle that grows and shrinks. They can't comprehend what a sphere really is, just like we can't comprehend a 4D hypersphere. Now flip it. If a 4D being interacted with our 3D world, it could pop into a closed room without using a door. It could see all of our insides at once. It would have godlike powers from our perspective. Chapter 5. The weirdness of the fourth spatial dimension. In a 2D world, a creature can only move in two ways, side to side or back and forth. It has no idea what up or down means because it doesn't exist in its world. Now, if you wanted to flip that creature over, like turning a pancake, you'd need to lift it into a third dimension. That's something it could never do on its own. Now imagine something similar happening to us. What if we were flipped through a fourth spatial dimension, not time, but a whole new direction in space that we can't see? According to the math, we would come back reversed. Our bodies would be mirror images. Our hearts would be on the right side instead of the left. All our internal organs would be flipped. This idea may sound like science fiction, but scientists say the math supports it. It makes us wonder, if a fourth spatial dimension really exists, could seeing it help us understand more about who we are and how the universe works? Or would it be so strange, so different from anything we know, that our brains simply wouldn't be able to make sense of it? Chapter 6. String Theory. The dream of unifying all forces didn't die, it evolved. String theory took the spotlight. Instead of point particles, string theory says everything is made of tiny vibrating strings. Their vibration patterns define the properties of particles. This includes gravity. One specific vibration represents the graviton, the hypothetical quantum of gravity. If true, we could finally describe gravity with quantum mechanics. But here's the catch, the math only works in higher dimensions. Depending on the variant, string theory requires 10, 11, or even 26 dimensions. Why? Because in fewer dimensions, anomalies and unwanted terms creep into the equations. But when the math is done in higher dimensions, everything fits together neatly. Chapter 7. Hidden dimensions all around us. Now don't expect to find a coffee shop with 12 different directions to walk around anytime soon. The extra dimensions that scientists talk about aren't big like the 3 dimensions we see every day: length, width, and height. Instead, these extra dimensions are very tiny and curled up, kind of like how a very thin piece of string is rolled up into a tiny ball. This idea was first suggested by a scientist named Klein. To help us imagine this, physicists often use a simple example. Think about an ant walking on a thin wire. From far away, the wire looks like a straight line, just one direction to walk along. But if you look very closely, the ant can actually walk all around the wire's surface, moving in a second direction. This second direction is hidden because the wire is so small. So even though the wire looks one-dimensional from far away, it really has 2 dimensions if you look close enough. The extra dimensions predicted by string theory are like that, tightly curled up at lengths close to the Planck scale, about meters. So small, they escape all current experiments, but they may shape the universe more than we know. Chapter 8. Seeing all dimensions at once. So what if you could perceive all these dimensions at once? It wouldn't just be like gaining a superpower. It would be a complete shift in your experience of reality. You might see every side of every object, inside and out. You could grasp connections that seem impossible now, like sensing time and space as the same fabric, or flipping through alternate versions of yourself. A 4D being would experience all of our 3D reality at once. If you could see in 10 or 11 dimensions, you'd probably transcend even time as we know it. Past, present, and future could appear as a single structure. Death might lose its meaning. Identity might expand beyond one body. But here's the paradox. Our brains evolved to perceive just 3 dimensions of space and 1 of time. Just like flatlanders can't picture a sphere, we might be forever blind to higher dimensional beauty. Chapter 9. The math behind the magic. Behind all this amazing science is pure math. It uses very hard ideas like metric tensors, modular forms, and theta functions. These math tools help us understand how things work deep inside the universe. Without them, many science discoveries would be impossible. For example, Ramanujan's theta functions are important in the math that supports string theory. These mathematical tools are not just there to look fancy. They are the essential machines that help physicists understand and explore the hidden dimensions of the universe. This is not just imagination or science fiction. It is about using equations that describe the universe much better when we allow for more dimensions to exist beyond the ones we can see. These extra dimensions help make the math work perfectly, giving us a clearer picture of how everything fits together. Chapter 10. Why it all matters. We might never experience higher dimensions directly, but their existence could be crucial to understanding why the universe is the way it is. From black holes to the Big Bang, from particle physics to quantum gravity, dimensions beyond our perception could be holding everything together. Some scientists are studying the idea that these extra hidden dimensions might sometimes connect or spill over into our familiar world when certain special conditions happen. If that is true, we could possibly find signs of these extra dimensions by using very powerful machines, like the Large Hadron Collider, which smash tiny particles together at extremely high speeds to see what happens. This could help us learn if these hidden dimensions really exist and how they might affect our universe. So, what would happen if we could see all dimensions at once? We would not just see the world differently, we would be different. We would know the unknowable, perceive the imperceptible, and maybe even begin to understand the ultimate theory of everything. And here's a question to leave you with. If you had a chance to perceive a higher dimension, would you take it, even if it changed you forever? Let us know in the comments below, and don't forget to like and subscribe for more mind-expanding videos like this. See you next time.